Alright, so in this video I'm going to look at question 1 from January 2012, Unit 4, and this one is all about electric fields. So the first question asks you to define the electrical potential at a point in an electric field. So the general definition is, so it's the work done. And was it the work done? Was the work done on each charge, so on per unit charge, and it's going to be positive, so we'd always define potential in terms of positive point charges, and it's going from infinity to a point. So that's essentially the definition, and this is one of the parts of Unit 4 that you just have to know your definitions. So it's the work done on each positive unit charge going from infinity to a point. Okay, so let's look at applying some of this. So the electrical potential at point L due to the charge is 3.0 volts. Calculate the magnitude of the charge, expressing your answer into an appropriate number of significant figures. So let's remind ourselves how we calculate potential in an electric field. So we're going to have 4 pi E0 R. So this is just inversely proportional, it's not an inverse square law. So we need to rearrange it to give us Q, like this. So then in terms of stuffing the numbers in, it's going to be 3.0 times 4 times pi times the value which is in your formula sheet, 8.85 times 10 to the minus 12, and then times the distance, which is 0.30. And when we do that, we'll end up with a number to the correct number of significance, 1.0 times 10 to the minus 10 coulombs. So checking significant figures, this number you're given in the question is 2 significant figures, this number you've used is 3, this number you used is 2, so we're going to give it to 2 because that's the smallest number of significant figures you've got in the question. Show the electric potential at point N due to the charge is 1.0 volts. So essentially, if you remember that the potential is Q over R squared, like times a constant. So when R equals 0.3, V is was 3.0. So if R is now 0.9, that's multiplied by 3, so V would be divided by 3, so it would be 1.0 volts. So essentially we're looking at the new potential is going to be the old potential divided by 3, because we essentially tripled the radius here. So then it's asking you to show the electric field strength at point N, which is midway between L and N, is 2.5. So making sure we're still using our uniform field equations here, so 4 pi E0 R squared. So let's put the values in. So we know it's 1.0 using the unrounded value for the charge. And we have 4 pi times 8.85 times 10 to the minus 12. And then midway between there we'd have a distance of 0.60 squared, which comes out as 2.5 times, not times 10 volts per meter, or you could also have had that force per unit charge, but essentially this is the answer you should end up with. Okay, so we've got R and S, two parallel plates, so we're looking at a uniform field here, 0.6 apart, potentials at 3 and 1. So it wants us to sketch the electric field showing its direction. So the field goes from the most positive to the least positive, and the field line should all be parallel. So essentially what we should have is like this. They should be equally spaced and parallel and going from most positive to least positive. Those are the two things we're going to need. Point T is midway between R and S. Calculate electric field strength. So field strength in a uniform field is V over D. So V in this is going to be 3 minus 1 because that's the potential difference. D is 0.6, and so we end up with 2 divided by 6 times 10. So 20 divided by 6 gives you 3.3 volts per meter as your unit of field strength. So let's scroll down and look at the last one. Parts B3 and C2 involve electrical field strength at the midway between potentials of 1.0 and 3.0 volts. Explain why the magnitudes of these field strength are different. So in terms of this, when we were looking at question B, we were looking at a radial field, whereas when we were looking at C, we were looking at a uniform field. So essentially that's the difference between the two. When we're in this question here, this is a uniform field equation, so you'd use that then, whereas in B we used the inverse square law, so that's showing we're using a radial field. So that's the end of the electrical fields question, so this is where I'm going to stop this video.